Welcome to a screencast where we will go over the answers to the fourth practice exam. Question number 1, we have a reaction. We have a rate at which the product is forming. What's the rate at which the reactant A2 changes? Well, the product is forming at a rate of 6.4 times 10 to the minus third molar per second. And this is AB3. Now, from the stoichiometry of the reaction, for every 2 AB3s that form, we have 1 A2 that's reacting. We'll put a negative sign there to indicate it's reacting. And that converts from AB3 to A2. And that means that we have half as much molarity per second change of concentration. So 3.2 times 10 to the minus third molar per second, with a negative sign indicating that it is decreasing as it changes. If the concentration of A is changed and that doesn't change the reaction rate, that of course means that we have a 0th order reaction in terms of A2. If it was first order, changing the concentration, the reaction rate would change in the same manner. And if we change the concentration of A2 and the reaction rate changed in a squared manner, that would be second order. What we can do to make this reaction proceed more quickly is we could increase the temperature. We could add an appropriate catalyst. And note the catalyst has to be one that works with this reaction to speed it up. So catalyst would decrease the activation or provide a pathway with a lower activation energy. Increasing the temperature means the molecules collide on average with more kinetic energy, and more molecules have enough kinetic energy to overcome the activation energy. And then in general, we can also speed up a reaction by increasing concentrations of reactants. But in this case, we know that the concentration of A2 doesn't change the rate of the reaction, so we're left with the only possibility here is increase the concentration of the reactant B2. Now next we can look at question number 2. We have a reaction and some initial rates data for this reaction. 3 different trials changing the concentrations of the reactants and seeing the effect on the rate. And to start, we know that the rate law for this reaction is going to be that the rate equals some rate constant K. Oh man, come on. Really, can we? Okay, so question number 2, we have a reaction. We have some initial rates data. So for 3 different reaction trials, we have concentrations of the reactants and initial rate values. So to determine the reaction orders, we first note, of course, that the rate law will have the form rate equals some rate constant K times the concentration of the reactant H2 to the some power X times the concentration of the other reactant NO to some other power Y. And the orders, or the powers X and Y, are going to be either 0, 1, or 2, and we'll determine those by interpreting the experimental data. Now, if we compare experiments 2 and 1, what we note is the concentration of NO stays the same between the 2 trials, but the concentration of H2 is twice as big in experiment 1 as it is in experiment 2. And we note that the rate is twice as big as in experiment 2 as it in experiment 1 as it is in experiment 2. And so what this tells us is if we keep the concentration of NO the same, that means this isn't changing. And if we increase the concentration of H2 by a factor of 2, and that has the result of increasing the rate by a factor of 2, then that must mean that this exponent x is equal to 1, and this reaction is first order in H2. This is direct proportionality. If we increase the concentration by a certain factor and it increases the rate by the same factor, then that means that the exponent is 1. Now for the second determination, reaction order in terms of NO, probably best if we compare experiments 1 and 3, trials 1 and 3. And we note that between trials 1 and 3, the H2 concentration is the same, but the NO concentration is twice as big in experiment 1 as it is in experiment 3, and that has the effect of making the initial rate go from 6.0 times 10 to the minus 7th to 2.4 times 10 to the minus 6th molar per second for the first reaction. Now, let's do this one the other way. Rather than just sort of thinking it through, let's actually grind it out by making a ratio of rate laws for experiment. And let's do experiment number 1 over experiment number 3. And for trial or experiment number 1, we know that the rate is equal to 2.4 times 10 to the minus 6th molar per second. We know that that's equal to a rate constant times the concentration of H2, which is 0.0100 molar, and we've already determined that's first order, and then times the concentration of NO, which is 0.0250 molar, and that is to the Y power, which we're going to determine. For the third trial, the rate is 6.0 times 10 to the minus 7th molar per second. That's equal to the rate constant K times the same concentration, 0.0100 molar of H2, and then times the smaller 0.0125 molar concentration of NO, and that's the Y power. And if we take these two equations and divide one by the other, we still have an equality, and we note that what ends up happening is K cancels. 0.1 to the 1 cancels, and 0.025 over 0.125 is the same as 2, or 2 to 1, to the Y power, and 2.4 times 10 to the minus 6 divided by 6.0 times 10 to the minus 7th works out to be 4. So we get 4 is equal to 2 to the Y, and that means that Y must equal 2, and this process is second order in terms of NO. If this hadn't worked out really nicely, we could solve for Y by taking the log of both sides of this equation and solving that way. So wanted to make sure this reaction was analyzed two different ways. One just by looking at the factor increases, and the other is by making a ratio of these rate laws with the specific data for each experiment. And you can analyze it either way to get to the result. Okay, so the next part we are going to find the value of the rate constant K using the experiment 1 data. What we know, of course, already is that the rate law is rate equals K times H2 concentration to the first power times NO concentration to the second power. So that means, of course, that the rate constant K is equal to the rate over the concentration of H2 to the first power times the concentration of NO to the second power. And if we plug in our values, what we have is the rate is 2.4 times 10 to the minus 6th molar per second. That's from experiment 1. And our concentrations are 0.0100 molar to the first order for H2, and then 0.0250 molar, and that's squared for NO concentration. And then what that equals numerically, we get 0.38 to 2 sig figs. And then we note that molarity on the molarity per second in the numerator, and one of the molarities in the denominator will cancel. That leaves us with per second, which we could write as seconds to the minus 1. And then it leaves us with the molarity squared in the denominator, which is also a negative exponent then, molarity to the minus 2. And so our k value is 0.38 seconds to the minus 1, molarity to the minus 2. And then last, the complete rate law for this reaction is that rate equals, damn it. So last is to get the rate law for this reaction. And the rate law will be rate equals k times h2 to the first times no to the second, but with the known value of k as being 0.38 seconds to the minus 1, molarity to the minus 2, and then times h2 to the first order, or to the first power, times no to the second power. And that is our rate law for this experiment. Okay, next up is question 3. And if we take a look at question 3, oh, come on, really? You son of a gun thing. Okay. So next we'll take a look at question 3. We have a reaction and we're told it's first order and we're given a rate constant value, and we want to find the concentration after some time has passed given an initial concentration. Well, since it's first order, that means we use the first order relationship, and in the case of pH3, what that means is that the concentration of pH3 at whatever time we're interested in is equal to the concentration of pH3 initially at time equals 0 times e to the minus kt. And the initial concentration of pH3 is, of course, 9.4 times 10 to the minus 3rd molar. That gets multiplied by e to the minus, and we're going to have all this stuff in the exponent. K is 0.0198 per second times t, which is 5.00 minutes. And now we note that minutes and seconds aren't the same units, so we're going to have to do a conversion. And 1 minute, of course, is equal to 60 seconds. And so that means minutes is converted into seconds, and then seconds and per second will cancel. And so then when we plug the values in and calculate, what we end up with is pH3 concentration is 2.4 times 10 to the minus 5th molar for our answer. All right, question number 4. We are given a reaction with progress of reaction, and we're going to determine the order and fill in the time in an appropriate picture in the last box and explain our reasoning. Well, what we note here is that we have 1, 2, 3, 4, 5, 6, 7, 8 x2s to start with. And then after 3 hours, we have 1, 2, 3, 4 x2s. So it's decreased by a factor of 2. So half as much. And then after 6 hours total, we have 2 of these x2s. And so we notice it's decreased again. And once again, it's decreased by a factor of 1/2. Okay, well, what does this mean? Well, if we have, how much time it takes for half of the substance to react is what's called the half-life of course. And in this case, we have a half-life of 3 hours for going from 8 to 4, and then we have a half-life of 3 hours going from 4 to 2. And if the half-life is constant, that is a characteristic of a first-order process. Only first-order processes have a constant half-life. So that means it's a first-order process in terms of X2. And then what that means is if another 3 hours goes by, so if we go to 9 hours, then it's going to decrease by a factor of 1/2 once again, which means we'll only have one X2 left. So there is an X2, and then all of the other ones are going to be just individual atoms. And that's going to end up being a total of, I think, 14 of them left as dissociated or formed as dissociated atoms. Question 5, we have a reaction that is second order, and we're asked how long it takes for the concentration of the reactant NOBr to decrease a certain amount. Well, since it's second order, we have a second order relationship that we will need to use, of course. 1 over the concentration of NOBr, our reactant, at time t is going to equal kT, the rate constant times the time, plus 1 over the concentration of NOBr at time 0. And we are solving for time, so to solve this equation for t, that's equal to 1 over k times 1 over the concentration of NOBr at time t minus 1 over the concentration of NOBr at time 0. And if we plug in our values, K is 0.80 and the units are per molar per second, and we have 1 over that. And then that's times 1 over NOBr at time t, so that's 0.021 molar. And then we subtract the 1 over concentration of NOBr at time 0, which is 0.186 molar. And then we just do the math on that, and that works out to be 53 seconds. Next, let's look at question 6. We have some concentration time data for a particular reaction, and we're going to determine the complete rate law for this reaction. Well, of course, what we know is that in general, the rate law for this reaction will be rate equals K times concentration of XY2 to the sum power, where that power X is either equal to 0 or 1 or 2. And if we're given time versus concentration data, we determine the rate law, or first of all the rate orders and then the rate constant, graphically. And what we know is if we have a 0th order rate law in terms of XY2, then what that means is that the concentration of XY2 at some time t is equal to the negative of the rate constant times the time plus the concentration of XY2 at time 0 initially. And if we note that if we let time be our X value and concentration of XY2 be our Y value, then this is a straight line with slope of negative K and Y-intercept of XY2 concentration initial. So if we were to graph concentration of XY2 versus the versus the time, if we get a straight line, then this would mean it's 0th order, and the slope of the straight line would be negative k. Well, we do the graph, and we end up getting a curved line. So this is not linear, and since it's not linear, then this relationship we postulated doesn't hold, and what we can conclude is this is this is not a 0th order process. So it's not 0th order. We can cancel that one off, and we move on and try the next one. If it's a 1st order process, then the ln of the concentration of xy2 at time t is equal to negative kt plus ln of concentration of xy2 at time 0. And that, of course, would mean if we were to graph log of concentration of xy2 versus, well, that was a little bit sketchy there. Let's make that a bit straighter. If we were to graph the concentration of xy2 versus time, then we'd get a straight line. So same thing as before, x and y, slope and intercept. And so a graph of t versus ln of y2 would give us a straight line with a slope of negative k. And if we do the graph of this, turns out we get a curved line as well. So once again, this one's not linear. And since it's not linear, we can conclude that this is not a 1st order process. Because if it was 1st order, we'd get a straight line if we graphed ln of xy2 versus k. Well, it's not 0th order, it's not 1st order. That pretty much leaves us with 2nd order. But we're going to have to confirm, and we're going to also need a k value. So if it's 2nd order, then the relationship between xy2 and time is 1 over xy2 at whatever time is equal to positive of the rate constant k times t plus 1 over concentration of xy2 at time 0. Once again, this is a y equals mx plus b relationship if we graph x as our t and y as our 1 over concentration of xy 2. So this time we're going to graph. This time we are going to graph 1 over concentration of xy2 versus t and see what happens. And this time, if we plot our data points, what we end up getting is a pretty straight line. So this one is linear, so that means it is 2nd order. And then the slope we get from this straight line turns out to be 0.026, and that of course is our k value. So we have a 2nd order rate law, so that's our x. We have our k value of 0.026, so this means our rate law is rate equals 0.026 times the concentration of xy2 to the 2nd power. And then, of course, don't forget, the rate constant has units, and this is going to be molarity to the -1, seconds to the -1. So that is our rate constant k, and that gives us our rate law. And just as a quick reminder how you get the units, if we know that it is 2nd order, so we know that rate is equal to rate constant k times concentration of, in this case, xy2 squared. If we solve for k, then k is equal to the rate over the concentration of xy2 2 squared. And the rate will be in units of molarity per, well, we were doing second for our time. And the concentration of xy2 is molarity, but that's squared. And then what that means is molarity per second. One of the molarities molarity cancels with one of the molarities in the denominator, and then this gives us 1 over seconds, and then over molarity, which is molarity or to the -1 as well. And so that shows where our units come from.